So I'm going to start with some review just to highlight some aspects of what we talked about last week on Wednesday, and actually from my the lecture and discussion with you and your comments, I was thinking of a way to make it clearer and much better. So this is already updated on Canvas. So one thing that actually took a long time to do is special case. What if you have the surface is the graph of function? So that was a recurrent theme for the examples we have done. And I was thinking it's best if we settle it first. I did that at the end last class, but we need to make it sure it is clear. So here we have a surface S. So we have surface S. Oops. As soon as I can get my, this one doesn't work here. So we have surface S here, and it is a graph of function defined by z equals gx of y. Can you extend today's point to Wednesday? Yeah, I can, for the homework assignment, I can do that. The idea is, what's the easiest way to calculate the double integral of the curve? It's actually more efficient to do it when you have the graph of a function than found in the line integral. So S is the graph of z equals gxy, like for example, the equation of a plane, you transform it to z equals something. And the d is the projection onto the xy plane. We need that. This is from chapter 7. So if the curve f is equal to three functions p, q, and r, then from what we did in chapter 7, the double integral over the surface S of the curve f is the integral over d here on the xy plane, the domain. And so we don't have to worry about the change of variable and finding t sub u and t sub v. We have that formula for it already done here. We can do even better. Most of our cases, we've seen an example. What if curve f equal to 0, 0, r? In this case, there is no p and no q. See, there is no p and no q. So we end up with just the double integral of r dx dy, which makes it much easier to compute whenever we have the graph of a function and the curve give us the first component is 0 and the second component is 0. So that's what we use for the basics, at the basis for most of the examples we have done. So here, just highlight this, what I wrote like this. So we did that for this example here. We have the plane, the surface is the plane y plus z equal 2, which means z equal 2 minus y is the surface. And it's inside the cylinder. So we can do it now faster, which is the first you compute curl, and curl has 0, 0, and r. So this is even more perfect because in this case, z, the surface is the graph of function. So we can go the double integral of the curve f. It's going to be the double integral over d of just r dx dy. We just need to find d, which is the projection on the xy plane. So the projection of that surface on the xy plane inside the cylinder, so it gives us x squared plus y squared equals 1, and so on. So this is mostly a shortcut for this. Any question about that particular shortcut? Whenever we have curl is 0, 0, r. This is another example here. Second one, 0, 0, r. And the surface is the graph of function. So we're going to just take the double integral of r. So I see the chat, question about them, recording. Yes, good. I think I'm recording now. Yeah. So in the chat, I'm going to put the link to this PowerPoint on the chat. It's also the one you have, it's already posted on Canvas. So the good news about this section 3 of chapter 8, it does not add more things. For example, we've seen that Green's theorem is a particular case of Stokes theorem. So basically, we can use Stokes theorem all the time. Green's theorem becomes a particular special case of it. Conservative field is allow us to connect even more and simplify more the calculations of double integral and a single integral. So the idea behind section 2 is the double integral, Stokes theorem, equal the single integral. But for double integral, we have to calculate the curve. When you have the graph of a function as the surface, and the f is relatively nice, when you take the curve and get something simple, it's much better to use the double integral. If we have the surface that is not the graph function or the curve is very complex, then it's much easier to use the single integral to calculate the double integral. So whatever easy, we use it to calculate the other one. Section 3 gives us another way to make that calculations even easier. So easier to calculate the single integral. The single integral can, along the curve, can be complex. And here it allows us to do it, to calculate it when we have some nice functions and certain conditions. Okay, so some motivation first, some reminder. That's what we did. So this is Green's theorem. The double integral equal the single integral. And sometimes the single integral is difficult to find. So it's easier to use double integral. Sometimes it's the vice versa. And now we're going to see whenever we need to find this single integral, it will be difficult to use double integral, but it will be something else that we can find it directly without using double integral. Another way to say it, we can use the conservative field to calculate the single integral, which allows us to calculate the double integral. And this is again the same thing. The curve double integral would be equal to single integral, and the single integral will be easier if we know that f is conservative. Okay, so this is actually the definition of conservative. And when you go back reviewing the PowerPoint here, you can just look at the first 2 slides, give you an overview. Okay, motivation. The motivation behind this is the fundamental theorem of line integral, which is similar to the fundamental theorem of calculus. Basically, whenever we have f equal gradient of a little function f, scalar function, the single integral becomes just f applied at the boundaries of the boundaries of the line, the space curve. So this is similar to the fundamental theorem of calculus, and this is something we've seen in the previous chapter. We're going to use that here. So basically, the question becomes: so the integral will depend only on the initial point and the final point. Another way consequence of that is that the line integral will not depend on the path. So to be independent of the path. What this means is that we can pick any easy path from one point A to one point B. For example, we can pick a straight line. It's easy to parameterize rather than a curve that can go all over the space. So the gradient field, as you know, they are important. This is gradient. So we talked briefly previously about V or minus F represent the potential energy of a gravitational, electric, and so on. And then we talked a lot about an example, which is F, which is the potential energy of the function F, which is the force that represents the vector field force of attraction, gravitational attraction. I'll just give you here that they exist and the relationship to physics. So we're going to call a vector field to be conservative if it is the gradient of some scalar function. If that happens, we know what we've seen before, that the integral will be independent of path, so we can pick easy one. And little f is called the potential function of f. So this is an example here, what we've done also before, where gravitational field f, so we use this little f, we take its gradient, we can end up with taking the gradient of little f, we get. So when are vectors field gradients? We need to determine that. If we find that, then we can look for them. So we have two-step process. Decide, yes, this is conservative field. If it's conservative field, then let's find the scalar function, little f. So main theorem, only one main theorem here, this one. It has 4 parts, but those 4 parts, they're all the same. One of them is, it is all the same, that says, what is vector field? If we satisfy one of them, we have the other ones. So one of them is the integral over any closed curve is 0. Then it's conservative. And vice versa. If we know it is conservative, the integral will be 0. We don't have to calculate it. The other one is dependent of the path. So independent of the path, doesn't matter what path you have, as long as they have the same endpoint, the integral is the same, which is exactly the one we've seen before. The third one, f is a gradient. So f is a gradient of some scalar function. So whenever we have one of those, we have the 2 others. And the third one, which makes it more interesting, like a test. The curl is 0. Think about it as a test. How do I know something is conservative? If I tested, take the curl of f and it's 0, I'm done. I have this, I have this, and I have this. And the curl is just computational one to work with, easy to do. Yeah. Wow, this is more mathematical conservative than, yeah. How you know it's very well. I don't know about that. Made me funny, but I didn't expect that comment on the chat. Okay, but here's not going to help you. You have to do the calculations. So for the proof, I'm not going to go over the proof. The proof is in the textbook. Actually, I often mentioned actually highlight of the proof by talking independent of the path. And you can choose an easy path between 2 points rather than picking one that's difficult, etc. So before I go over applications, let's see some examples. One thing I spoke about in a previous section just today is about application, that the curve gives us the circulation. So this is the curve, give us the circulation around here, and the axis. A second interpretation is the motion of a circular circulation. So basically here, we're going to see that at the end of the last section, that whenever the integral over a curve, it means that there is some circulation here. So, for example, if we have the line integral be 0, we know that it's not going to lead to any circulation or rotation. So, what I'm calling it is, so f is arotational. Rotational means curve f is 0. There will be no rotation. That's the notation and the meaning of that. I found the scalar, this is an example, scalar potential of f. So basically find delta of f equal f. But before that, before we need to check that F is conservative field. So to do that, we're using the last one, which is part one. I check curve F equal to 0, then F is a conservative field. If it's not 0, it is not conservative field. Very easy, simple test. So just computational. It's not always easy, but it's computational. Here we go. Gradient, as you know, we have to put ijk. We have to put the partial derivative, and we calculate these. So calculate determinant. So this is P, Q, and R, and we calculate determinant. So I leave it here for exercise. Trust my calculations is correct here. So we get 0, 0, 0, so it's 0. Therefore, it is conservative. So implies find F now. Part two. So this process is computational. The next process is also computational, but requires multiple steps. And it's different for each case. We need to find F such that the field, the vector field equal the gradient of little f. So always we're gonna write what F is, just remind you what that is. And we're gonna write the meaning of the gradient. So before doing that, actually, I'm going to show you method one because the textbook talks about this method one. It's not the best method, so it's not used as much, but I want to show it to you just in case you read the book and you see it, you know where it's coming from. So this one, it says little f is exactly these integrals. However, this is not always recommended because these integrals can be complex. You see here we have x, here we have x and y, can a little bit be complex to work with. So if it works, like in this case, it's going to work, go ahead. However, we have a better method that works all the time rather than this one. So here is just for your information. So our f, this is our f1, we'll call it q, this is f2, this is f3. We calculate replacing x by t, y by 0, and z by 0. So we get 0. This works fine. So this one works fine. And normally I need to add a constant. Sorry about that. No, there's no constant because of definite integral. And we're done. So, however, this one is not always easy that way. So it's best to use method 2. It's more natural than this one. Okay, this is the method we're going to focus on doing. Find f such that f equal this. So we're going to write what the gradient is. So we don't know what f is. So this is the gradient of f equal f leads to us to these 3 equations. So the partial derivative with respect to x should be equal to the first one. Partial derivative with respect to y should be equal to the second one, and partial derivative of f with respect to z should be the third component of the vector field. And we're going to work with that. So this is almost similar to something you probably worked on in multivariable calculus. So first one, partial derivative of little f of x equals to y. We take the integral both sides. I'm not going to write the integral, just the antiderivative. So f, it's going to be, remember f is a function of x, y, and z. It's going to be that y is a constant, x times y. And the most important part, plus some constant. This is constant with x, sorry, with y and z. Y, and z, because y and z are constant with respect to x. So it's very important to include y and z here, because the derivative of that function with respect to x will be 0. So we add in a constant, we take the antiderivative. Question about that part? Next, I'm going to take the second one. I'm going to write it down. Partial derivative of f with respect to y equals to the second component of the vector field. However, this time we're not going to take the integral. Actually, what we are going to do, we already have f here. We're going to take that f and take its partial derivative with respect to y. I'm doing here. Take partial derivative of this f with respect to y on the left side. So partial derivative xy with respect to y gives me x. And this function h1 is going to be just partial derivative of h1 with respect to y. I don't know its value. And I keep the right side the same. So I'm just calculating this part, left side. Next, I simplify, right? There are x here and x here. All right, what's left? So now the problem is finding h1. h1 is a function of y and z. And you can see here partial derivative give us y and z. So how do you find h1? You integrate. Find the antiderivatives. The integral of h1 with respect to y give us h1 on the right side and the left side, and the integral of this with respect to dy. Z is a constant, so it's actually using y, so this is using the change of variable u. So sine of yz, so this is du. Du equals z, dy works perfectly. So we have h1 equals sine of yz. However, plus constant. Remember actually the constant here? We take antiderivative constant with respect to y, thus it's h2 of z. Will it continue in z? There is no x, there is only z left. And finally, we're going to put all this together back to f. F now, we're building it little by little. We have xy first. We added this value, but we have h1 now contains function h2. So you can imagine the next step is going to be is to continue doing the same thing again and again. Using the third equation, this equation. Okay, I'm going to put the equation here. We're going to use this. So same thing as before, I'm not going to take the antiderivative. I already have f. So let's bring f here. I'm going to take the partial derivative of f as given here and write it on the left side. So the partial derivative with x, y is going to be 0. This is 0. Partial derivative with respect to z of sine yz give us y cosine z plus the partial derivative of h2 with respect to z. We don't know what that function is. And we solve the equation. The right side remains the same. These are the same, which means partial derivative of h2 with respect to z equal to 0. Therefore, my h2 must be a constant. This is the constant. And we're done. I just need to go back and put that constant c in the formula for f, and done. What's nice about this one is not only gives us one function, little f, give us many, because as long as we change c, we get another one, and this one works. So this one has multiple steps than the previous method. Again, the first method does not work all the time. This one works all the time. You're just repeating the same process again and again. Questions about this? So I'm gonna give you more examples at the end of class today. What happens if you have the planar case? What happens if you have, this one should be supposed to be animated. If we have f equal just 2 p and q. In this case, we know that the curl of f, this is curl, is just given by these mixed partial derivative. And the condition curl f equal to 0 is just mean when we switch p is the first variable, goes with y, and q is the second variable, goes with x. This is the second, goes with the first variable, and vice versa. They must be the same. So it's easier test than the curl for function for a vector field in with 3 variables. Okay, this is the corollary, just saying that, and you just need to test this, and we're done. And you can imagine finding the function, potential function f here requires only 2 steps because we only have 2 variables. So first thing is we need to determine whether or not the vector field is conservative. This one is just using 2 variables. This is our p, this is our q, before we can try to find the scalar function f. So partial derivative with respect to p, partial derivative with respect to q, we switch them. P goes with y, q goes with x. They are different, therefore not conservative, so we stop there. That's basically finding some integrals with this one using conservative field theory will not work. So I'm gonna stop talking here and give you this one. So I'm gonna make pause here and give you breakout rooms, pause the recording, and open breakout rooms. Okay, welcome back, everyone. Okay, this one actually does not require as much time. You have time to reflect on it. So we have our p and q. We just need to check that partial derivative of p with respect to y equal to partial derivative of q with respect to x. If it is equal, it is then conservative field, and in this case, we need to find little f. If not, we stop there. So partial derivative of p and q with respect to x, they are different. So here it's not gradient. So we cannot have all these benefits of being gradient. This is the same question. I'm gonna do the first part and I'll give you time to the second part. First, let's check that this is indeed gradient. Oops. So we take the partial derivative of p with respect. So this is slide number 20. So we take the partial derivative of p with respect to y. We compute partial derivative of q with respect to x. They're exactly the same. So yes, we need to find little f. So I'm gonna again open a breakout here and give you probably more like 4 minutes for this one. So I'm gonna open the breakouts, Same breakout rooms. I'm gonna pause the recording after that. Okay, welcome back. So here after testing, it is the curl or partial derivative of p with respect to y equals partial derivative of q with respect to x. We're gonna follow the same main process of finding the potential function little f. So first, the gradient of f, as you know, is partial derivative of f with respect to x, partial derivative of f with respect to y. So the first one has to be with the first one, second one has to be with the second one. Start with the first equation. Taking the integral both sides. Y is a constant, so we only have the integral of x to x, which is x squared, plus this is constant for x. So we only have one variable left, y, so we don't need h1 and h2. Next, we're going to take the second equation that involves partial derivative of phi equal to the second portion here. But this time we do not take the integral, right? What we need to do is we're going to use the fact that we already know f. We're going to take the partial derivative of that f with respect to y. Derivative of cosine of y is minus sine of y. Derivative of h is derivative of h. We do not know what h is. On the right side remains the same. Then we perform some simplification. Here are the same. We have left partial derivative of h with respect to y equal to 0. Taking the integral, give us h is exactly just constant. I'm going to put everything back together. So little f is x squared cosine of y plus constant c. Questions about that particular problem? Or comments in the chat? Seems straightforward. You need to do a few of them. I assigned a few of them on the homework assignment. Example number 4. Example number 4, we finally go into here. So what we did so far is determining when vector field is gradient. If it is by finding the curl equal to 0, we're going to find the potential functions. Now for this one, we try to see how we can use it, but we're going to use that information. So imagine I need to find, compute the integral of this function over C, or compute the integral over S, any surface S of curl F ds. So F here looks, it's going to be a little bit messy. It doesn't matter what the surface is, especially if the surface is very complex. So in this case, it's much better to say this one is equal to Stokes theorem. It's equal to the line integral over the curve C. The curve C is given to us. It's not easy one. So not easy one. It has exponential, it has sine. If you do the substitution, imagine the substitution of x here and y here. So you're going to have exponential, we're going to have cosine of sine. It's going to be a very messy function. So our hope here to be able to solve this is really ff is equal gradient of f. That would be nice, because in this case, we don't care about the curve. The path does not matter. in this case, we're going to use the fact that the integral of f ds is equal to just little f of the endpoint minus little f of the initial point. And that's it, we're done. So let's hope this is happening, and it should be happening because otherwise there is no way we can find that integral. The slides for second example were broken. Okay, I will try to fix that. Sometimes when I move things from the computer to the shared drive, it does not transfer well. I will fix that. Okay, so let's work on this. So my hope is this. If I do that, we get through. So this is f. We're going to do the same idea. Take the partial derivatives. They're exactly the same. So yes, that's a good thing. My next step is finding f. Actually, this is exactly the one from example number 3. So I didn't want to do it again. So it's exactly number 3. Number 3, find f. F. This is f. So now to calculate the double integral of the curl of the vector field, or to calculate the single integral of that vector field, I don't need to know the parameterization of the curve or the parameterization of the surface. I just need to use the fundamental theorem of line integral. This one. So I see your comment about broken slides. Yeah, I have to go directly on the shared drive and see what they look like. Sometimes, again, we need to change from PowerPoint to Google Slides. Does not work very well here. Probably I had too many animations in there. Okay, any questions about this process so far? Why it's good to find it is a gradient. So we don't care about the surface parameterization. We don't care about the curve. We care about the initial and final point of the curve. So the curve, remember, was very complex. But I don't need that because this is my curve. If I have to do any calculations from like we did in the previous sections of chapter 8, we cannot get through it. It's going to be complicated to do. So we just need to find C. It's going to be C of the end point, which is C of 2, because we have 2 here. And here we're going to do C of 1, because we're starting at 1. And we have our function f. We substitute function f. Let's go ahead and do that. And we're done. So this is really advantage of using knowing that it is gradient. Question about that part, other than the slides on the link on Canvas, broken because the way it changed. Okay. So most of the examples will be like this. Again, the homework assignment, check if it's a conservative field. If it is, find the potential function f. If you have a question that's asked calculate the integral or the single integral, we can use the fundamental theorem of line integral. Okay, to finish today's class, what happens if divergence of f equal to 0? So this is just additional information. We're going to talk more about divergence in the next section, section 4. Just saying here that if we have the curve of f equal to 0, f is conservative. Is natural question is, what if divergence of f equal to 0? Can f be the curve of a vector field G? The answer is yes. If divergence of f equal to 0, then f is the curve of another vector field. And this will come in play some later. So this is the analogy of the theorem we have, the conservative field. Oops. So we're not going to use it time being. We're going to use it for the next sections. I didn't include anything else. Yeah, that's it. I'm gonna make pause here and go over your questions and chat without having everyone recorded. Pause the